Let's do this big example practice problem here. So this one is 6.19. So it wants us to use the work kinetic energy theorem to solve all of these different parts. So I'm going to do A, C, and E, and then you're going to do B and D as practice. So I'll do A, C, and E right now and at first, and then I'll put the answers up on the board for B and D at the end, okay? All right, so the first part is a branch falls from the top of a 90-foot tall redwood tree starting from rest. How fast is the branch moving when it reaches the ground? We're going to assume air resistance is negligible. So there's no one pushing the branch down, there's no air resistance. It starts at rest, ends at the ground height of 0, and there's no springs. So what I'm left with here is 0 is equal to K2 minus UG1, meaning all of that gravitational potential energy I started with ends as kinetic energy. All right, so I have mgh equals 1/2 mv squared. The m's cancel. V is equal to the square root of 2g times h. So V is equal to the square root of 2 times 9.8 times 95 for the height of that. And if you type that in, you should get 43 meters per second. It's about 95 miles an hour. That stick isn't going to be going that fast because air resistance is going to be there. All right, so let's do one with some resistance. So I have a skier moving 5 meters per second. They hit a rough patch with a coefficient of friction of 0.22. And they're going to come to a stop, and they want to know how long does it take them to come to a stop. So no one's pushing on my skier. There is friction, however. The skier comes to a stop at the end, and they're moving at 5 meters per second at the start. Uh-oh. There we go. I almost sneezed on camera. And they're starting at 5 meters per second, and they're ending at rest, and they are staying on level ground, meaning their height at the start and end are the same, and so I'm going to call both of those 0, and there are no springs. So I'm left with work done by friction equals negative K1. All right, work done by friction, remember, the force of friction dot the displacement equals negative 1/2 mv squared. Notice these are vectors, so I need their direction. So the force of friction is pointing to the left. So if I was going to draw a free body diagram here, I have mg, I have a normal force, and I have friction. Okay. So I have a negative force of friction times S. So I've just put in the directions on those two forces. The S is positive. Start making my substitution. So this is kinetic friction. So it's mu sub K times the normal force times S. Normal force, all right, in my case, the normal force equals mg. All right, so I have negative mu mg times S equals my negative 1/2 mv squared that I brought down here. The m's cancel, the negatives cancel, and so now I just have to solve for S. And so S is going to be the V squared, which was 5 squared, divided by 2 times 9.8 times 0.22. And that should solve us for S. S comes out to be on this one 5.8 meters. Be careful when you're doing these. If you end up on an inclined plane for friction, remember you're going to have to solve for that normal force accordingly. Also, as you're doing this, the two number one errors I see is I see this negative sign get left out, meaning friction's working in the direction of the displacement. The other thing, as you're doing this little strategy here, your focus tends to be right here, and this S falls off the end. So be careful about that. All right. Let's do another one. I have someone on a toboggan, and they're sliding down a hill, and they're going to be going 12 meters per second at the bottom of this hill, and it wants to know how high is the hill. All right, so let's cross some stuff off. So it's going from one point to another. So all these we're doing the 1 point to a second point, work kinetic energy theorem. No one's pushing them, said it was a frictionless hill. They're moving at the bottom, they were stopped at the top. Potential energy at the bottom is 0 because their height is 0, but they do have potential energy at the top. So I'm left with 0 is equal to K2 minus UG1. So I have UG1 equals K2. Now this is pretty darn familiar to that one there, that all of the potential energy we start with turns into kinetic energy at the end. So I have mgh equals 1/2 mv squared. My m's cancel, my v is equal to the square root of 2gh. Whoops, I solved the wrong thing. We are solving for height. So then height is going to be v squared divided by 2g. So they're moving at 12 meters per second at the bottom of that hill. 2 times 9.8 on the bottom. So the height of this hill is 7.35 meters high. All right, so notice the pattern. So we start at one point, we go to a second point. We write out our work kinetic energy theorem, cross stuff out, solve. Same thing again, start at one point, end at another point, cross stuff out, solve. Just remember when we do work done by friction, we got to include direction on that force of friction, and when we're substituting, don't forget to keep that S on there. This was an inclined plane. Cool thing here, didn't need to know the angle of the incline, didn't need to know the length it went down in order to solve this problem. Now, if there was friction, yes, I would need to do a little bit more work on that. We do have an example coming up where we do that. So let's go ahead and write down those answers for your two problems. So B is a lot like A, it's just in the reverse. It's shot up and comes to a maximum height, and so that velocity for B is 101.4 meters per second. D is similar to this one, except for the patch isn't as long, and so it's going to have a speed at the end, so you are going to have a K2 in there. And so that speed at the end is going to be 3.5 meters per second, and that's for part D. All right, there you go. Give those two a try.